Dear all, I am Dr. V. Malati, Associate Professor, Department of ECE, SR University, Varangal. Today's video lecture is on simulation of pulse oximeter calibration and testing. So, in this simulation, we will get red PPG signal with noise. So, PPG means photolithosmography, and then infrared PPG signal, which is noisy. Both are graph of time versus voltage in amplitude, and then we will measure in the output red AC component, red DC component, and then infrared AC component, infrared DC component, and finally the ratio R is equal to red AC by red DC whole divided by infrared AC divided by infrared DC. So in this case, the pulse oximeter is used to measure the oxygen saturation, that is SpO2 of our blood, and it is assumed to be equal to 90% for normal. And why do we measure the oxygen saturation? It will give a measure of heart rate of the human. That is why we are doing this experiment. I have written the code in Python and I am going to simulate in the Google Colab. Now I am going to measure the share the screen. So we are getting the measurement and then red PPG signal noisy, infrared PPG signal noisy. And red AC component is measured as 0.01425. Red DC component is equal to 0.000056. Infrared AC component 0.02. And infrared DC component 1.19. Ratio is 0.8006. Estimated saturated oxygen content in percentage is equal to 90%, which is usual for the normal human being. So here the red and infrared. Suppose the hemoglobin is more, it will absorb more red, and if it is less, it will absorb infrared rays. Now I am going to explain the code line by line. Here, to simulate a pulse oximeter system, we have to process red and infrared PPG signal, and we have to estimate SpO2, that is oxygen saturation level. This experiment simulates red and infrared PPG signal. Then it adds noise. Then it filters the signal. Then calculates AC and DC component. Then it will compute a ratio of ratios or then estimates SpO2 using calibration equation. So we will get the expected output SpO2 value around 95 to 100. So we are getting 90%, so no problem. And then 2 PPG waveform, plot red and infrared. So simulated PPG signal, it will have DC component constant part, that is due to tissue, bone, non-pulsatile blood. And then AC component, pulsatile part, it is due to the heartbeat. Then red signal, red underscore DC is equal to 1.0. 0. Then red AC signal is equal to 0.02 into NP sine 2 pi 1.2 t. That is heart rate is equal to 72 beats per minute. Red signal is equal to red underscore DC plus red underscore AC. So total red signal is the combination of AC component and DC component. So what is red D underscore DC is equal to 1.0. It is the baseline. It indicates baseline. 1.2 hertz normally it is heart rate frequency. Since 1.2 hertz is normal, it is 1.2 into 60. It is a second I am telling. So when it is converted into minute, then 1.2 into 60. That is 72 beats per minute. So heart rate is equal to 72 beats per minute. And then 0.02. It is small in amplitude. 0.02 it is small in amplitude, that is pulsating part. Then final red signal is equal to DC and AC. So next one infrared. So infrared DC part is taken as 1.2 and then infrared AC part is taken as 0.3. Into NP sine 2 NP pi 1.2 into T. So, total infrared signal is equal to AC component plus DC component, similar to red signal, but it slightly it have higher DC component, slightly higher AC amplitude. So, this difference helps calculate oxygen saturation. Then we are adding the noise. So noise underscore red is equal to 0.005 into NP random dot RANDN LVNT. Then random noise underscore IR is equal to 0.05 into NP dot random dot RANDN LVNT. Now what is the meaning? NP dot RANDM, I mean random dot RANDN is it is generating the random noise. So amplitude is very small. It is 0.005 only. So this simulates motion artifacts, sensor noise, ambient light temperature. Ambient light interference. Then noise is added. Red underscore signal noise is equal to red underscore signal plus noise and red, and then IR signal noise is equal to IR signal plus noise IR. Now signals look more realistic than band pass filter. So it is 0.5 to 3 hertz for heart rate. So here define band pass filter, signal, low cut, high cut, Fs, order 4. So Nyquist 0.5 into Fs. Low is equal to low cut by Nyquist. So here 0.5 Fs is equal to Nyquist frequency is equal to Fs by 2. It is equal to 50 hertz. So here 0.5, so Fs by 2 is equal to 50 hertz. Low cut is equal to low cut by Nyquist. Why we are doing division by Nyquist? It normalizes the cutoff frequencies. So B, A is equal to butter, order, low, high, and butterworth type is equal to band. So what is the meaning here? Low is equal to low cutoff frequency divided by Nyquist. So in the same way, high cutoff frequency divided by Nyquist frequency. So B is numerator of the filter coefficient. A is the denominator of the filter coefficient. It is equal to Butterworth filter. Order always we are taking 4 and then low, high. So low value here it is determined. High value here it is determined. Then P type, Butterworth type of filter is equal to band pass filter. We are considering band pass filter. And then it will finally, after filtering, it will return the signal with the coefficient, numerator coefficient B and denominator of the filter coefficient A. So why do we apply filter function. It applies to the filter, but zero phase distortion cleaner output. And then 0.52 GHz YBR here already given 0.52 GHz. 0.5 hertz means it is 30 beats per minute in the same into 60. So in the same way 3 hertz means 3 into 60 180 beats per minute. So only heart related frequencies are passed. That is why. So lower cutoff frequency, higher cutoff frequency. So frequency components less than this one, 0.5 will be removed. In the same way, frequency components above 3 hertz will be removed. So those two are the stop band. But frequencies lying between 0.5 to 3 hertz are called as pass band. Next one, AC component. AC and DC component. Red underscore AC underscore value is equal to NP standard red underscore filtered. So IR underscore AC underscore value is equal to NP dot standard open bracket IR underscore filtered. So standard deviation is equal to pulsatile amplitude. It represents AC part. So DC means it is straight line. There will not be any peak. And then DC component is equal to red underscore DC value is equal to NP mean value red underscore signal underscore noisy. So the same way IR underscore DC underscore value is equal to NP dot mean IR underscore signal underscore noisy. So mean value normally we know it is baseline level. So it represents DC value. And then ratio of ratios. It is red underscore AC, AC component, red component AC value divided by red component DC value, whole divided by IR component AC value, IR component DC value. So why we are doing this? See, oxygenated hemoglobin absorbs more IR. Deoxygenated hemoglobin absorbs more red because it needs it. After getting diluted, the red color will not be dark in nature. That is why it absorbs more red. So the ratio gives oxygen saturation information. Now SpO2 calibration equation, that is empirical calibration formula. So SpO2 is equal to 110 minus 25 into R. This is an empirical calibration formula. It is commercial pulse oximeters use experimentally derived calibration curves. So typical output is around 95 to 100%. So if we display the results, print red AC is equal to red underscore AC underscore value, which already we have determined. It displays AC value, DC value, ratio R, then estimated SpO2. Then go to plot signal. So PRT dot figure. So 2, 1, 1. So it creates 2 rows, 1 column layout. So top plot is red signal, bottom plot is IR signal. So plot tight underscore underscore layout. It adjusts the spacing and plot dot show it displays the graph. So overall, what is the sequence PPG signal first taken from the body, and then we are adding the noise. Then it is applied to band pass filter. Then it is extracting AC component and DC component of both IR and red signal. Then it is computing ratio R. Then from that calculates SpO2. So this is the conceptual understanding of pulse oximeter, how it is working. So normally red light is 660 nanometer, and then infrared is 940 nanometer. So different absorption for oxyhemoglobin, that is HbO2, and then deoxyhemoglobin, that is Hb. So ratio method eliminates tissue thickness effect, then LED intensity variation. So these are all the effects from the pulse oximeter. So what we have here, the measured value of AC and DC value for both red and infrared we have taken. So we are taking the outputs, red signal included with the noisy and then infrared noisy. So here, what we first one, we have to download we have to import the NumPy library. So NumPy Python library from NP. And then we are taking the FSC and then we are taking the matplotlib.pyplot as PLD. So wherever we see PLD, it is able to plot the output, and then pyplot. So this is the module from which matplot library is imported, and it is used to take the output in terms of box plot or ordinary graph of one parameter versus another parameter, and then histogram. So like that, so many outputs we can draw. And here piece of anyway signals are taken from our body, so that signal functions, signal first from signal module we have to import the SciP library, and then signal functions. There are so many signal functions, but in this experiment we need to have butter and filter. So both are enough, so that they are taken from the library, say signal functions. So next one we are taking Fs is equal to 100, sampling frequency, number of samples taken per second. So it is equal to 100, and then usually we will take x-axis time. So line space, how it is taken, 0 up to 10. So 0 up to 10 means starting value 0 and ending value 10. This 10 is divided into so many parts. So how it is divided? 1 by 100. So 1 by 100 means 0.01. So after 0 we will get 0.001 and then 0.002. So up to 10. So very small time interval in between two points in the x-axis. Next one, we will simulate the PPG signals, DC component plus AC component, that's all. It is for red plus infrared, both signal is applicable. So red DC signal, we assume that it is 1, and then red AC signal, since it is a sine component, sinusoidal waveform, we will take the amplitude of 0.02 and sine 2 pi. We have to convert into angular frequency. So omega is equal to 2 pi f 2 pi 1.2 t. So it is very low frequency from our body. That too from heart, that is why 1.2. So it is standard value for all human, and then red signal is equal to so total red signal is equal to DC component in addition to the AC component. The same thing is applicable to the infrared also. So infrared DC component is somewhat increased value. So here 1, but here 1.2. So normally it is more, that is why amplitude is taken as 1.2 for DC. And then AC value is equal to 0.03, so slightly greater value, plus NP dot sine to, once again we have to convert into angular frequency, omega 2 pi f, so 2 pi f is equal to 1.2, same value into t. So IR signal finally it is the combination of DC value and AC value. So now we have to add because normally signal will not be taken into taken as input because anyway the noise will be included. That is why we have to assume for the red signal and IR signal, we have to add with some amount of noise, smaller amount of noise with the magnitude very small 0.005, and then noise underscore red is equal to 0.005 random RANDN length. So what is the value? Random numbers are generated, and then while sampling the same length as equal to original signal will be taken for the noise also. See, number of samples per second, if fs is equal to 100 for raw signal, the same thing is maintained for the noise also. So IR noise and red noise for both. That is why length in time. So time interval should be same time interval, and the segregation is also same, and fs is also same. That is why. The next one, red signal noise. So it is noisy signal, original signal added with the red noise. In the same way, original signal with the noise IR noise. So the input signal which is given to the filter will be finally red signal noisy, red signal IR signal noisy. Not red signal alone, IR signal alone, because definitely that noise will be added. In the same way, band pass filter, we are taking lower cutoff frequency is 0.5 and higher cutoff frequency is 3 Hz. It is for normal human being. That heart rate lies between heart rate frequency lies between 0.5 to 3 Hz. So below will be not allowed, will not be allowed, and above 3 Hz will be taken as noise. That is why they are removed. And then we have to define the band pass filter with the signal. So we know signal and then low cut. So already we will determine the low cut and the high cut, and then sampling frequency. Already we know it is fs is equal to 100, and then order is equal to 4. So for all BMI signal we are taking order as equal to 4 because higher order, if order of the filter is higher, then the filter will be steep, very smooth filtering will happen. That is why 1 normal, so 2 and 3 already it is higher order, and beyond that 4th order means still we will get the smooth filtering. That is why higher order filter is applicable here. It is for red filtered and then IR filtered. Both signal we have to apply. And then the filter aim is to generate the coefficients. So the coefficients means a numerator B and denominator A. So numerator low, numerator is B comma A, and how it is generated? Butter open bracket order. Order we know that it is 4. Low we have already determined low cut by Nyquist. So why we are Nyquist means half of the sampling frequency. Normally why we are following Nyquist frequency, Nyquist criteria we have to follow while sampling. If the sampling frequency is greater than or equal to 2 into maximum frequency content present in the signal. If it is so, the criteria is satisfied. Suppose if sampling frequency is less than 2 FM, then aliasing will be the effect. Now what is the aliasing? Aliasing means similar. So low frequency content will be similar looking like high frequency content. Actually the sampling frequency should be higher than or equal to. That is why aliasing problem will occur. This aliasing problem will be overcome by using aliasing filters. So to avoid this, when starting the sampling of the signal, we have to consider the Nyquist criteria. So the normalization for the lower cutoff frequency and higher cutoff frequency we have to perform, and the same thing is applied here, low comma high. And then Butterworth filter type is taken as band pass filter. So it will have lower cutoff frequency, upper cutoff frequency. Below lower cutoff frequency, all will be removed. And in the same way, higher than the higher cutoff frequency, those signal components will be assumed as noise, because noise means low in amplitude, but the frequency will be higher. So they are assumed to be noise, so that they have to be removed. So in between these two, that is the signals frequencies ranging between 0.5 to 3 Hz will be considered as pass band, and they are allowed to enter into the band pass filter. And finally, it is returning the signal with filter coefficients B, A and filter. Why we are doing filter? It will be, there will not be any phase distortion or time delay. So we are getting smooth, clean filtered signal. That is why we are applying the filter function. It will return the signal of such a good quality, and then red filtered is equal to band pass filter, red signal noisy. So on which it is applied, the noisy red signal will be applied to the band pass filter of cutoff frequency 0.5,3. Already we have decided. Sampling frequency FS, it is normalized. And then IR, the same, whatever processes we are doing for red signal, same thing is applied to the IR signal also. So band pass filter is applied to IR signal, that is noisy signal. It is ranging from cutoff frequency ranging from 0.5 to 3, and then sampling frequency. So now how to determine AC and DC components? So AC value is equal to standard value of red filtered signal. In the same way, IR AC value is standard value of IR underscore filter. DC value we know it is mean. Standard value means mean around the positive peak and negative peak we used to get. But mean value means there is no upper and positive going or negative going, and it is the standard reference line only. So red underscore DC value is equal to NP dot D, mean red underscore signal underscore noisy. In the same way, infrared DC underscore value is equal to NP dot mean and open bracket IR underscore signal underscore noisy. Now ratios of ratio, how it is calculated. The value is represented in terms of R. R is equal to AC component of red signal divided by DC component of red signal. So this value whole divided by AC component of IR signal divided by DC component of IR signal. So finally we have to from R value we have to calculate the SpO2, which is the oxygen saturation of the blood. So saturated, the percentage of saturated oxygen value present in the blood. So for this we have one calibration formula, standard formula. SpO2 is equal to 110 minus 25 into R. So R we have already determined. So we have to display the results. What are the values we determine? AC value for red, DC value for red. AC value of IR, DC value of IR. And R using the formula we have calculated, and then from this we have to calculate the estimated value of oxygen SpO2 using this formula. Finally, we have to plot these in the graph. So first one figure says 12,6. Now what is the meaning for 12,6? 12 with height is 6 and subplot. So along this we have to we are going to have only two graphs. So, two rows, one column. So, in that first position is red PPG signal. And then it is the graph of time versus red signal noisy. So, time, x-axis is time, y-axis amplitude in voltage. And in the second plot, two rows, one column, and second position, the same thing is for IR signal. So time, comma, IR signal noisy. So plot the title infrared PPG signal noisy, and then it is a graph of x label time in second, y label amplitude, and then tight layout. So each and every graph will be of equidistant, and they are located spatially with uniform space. So tightly fit, then chart show all are displayed. So it is the meaning of this PLT dot show. See, all the graphs are visualized in the graph. So all values are calculated and then it is seen. So with this we end this lecture. Thank you.